Morning, everyone. So yesterday we started reintroducing some of that equilibrium constant. Essentially, the Kw, the Ka, and Kb that we talked about yesterday was basically the Kc that we had learned from our equilibrium chapter. All we're doing, though, is we're applying it to very specific equilibria. So, for example, Kw was referring to a auto-ionization equation. This is going to become important in today's lesson here. Essentially, water has a slight ability to self-ionize. Water always regenerates some H plus and regenerates some hydroxide. If I write out an equilibrium expression for that one there, I go products over reactants. Essentially, it's going to be the H plus times OH minus. We do have a table that actually lists for you Kw values at a whole bunch of different temperatures. There is one temperature I want you to memorize it for. This one here experimentally is 1 times 10 to the negative 14 at 25 degrees. This actually, when we start introducing our pOH scale, this actually puts 7 as a dividing line. That's only true at 25 degrees, right? So it gives us a nice mathematical link here. Anytime you know the H plus, I can just punch it through this equation and I can find the OH minus and vice versa. At first, we did questions where I would actually change temperature. We know this auto-ionization equation is actually endothermic, so the heat term is on the left side. We did an example where if I increase the temperature, the water would actually shift towards the right. We're going to produce 1 H plus, 1 OH minus. We pick up H plus and OH minus at the same rate. We're going to stay neutral, and the Kw could actually increase. More often than not, as we're going to see in today's lesson, usually we're going to be at the same temperature. Usually we actually hit the same constant. For two numbers to always multiply to give the same number, in fact, as I get more acid particle, I would expect to get less OH minus particle. So sort of those are the two styles of problems. If you change temperature, they're going to change in the same direction. If you change just, I add acid or add base, I would expect an inverse relationship. Okay? So just for a quick practice here, just practicing writing like these Ka, Kb style equations here. I want you to write the Ka expression for acetic acid. Right? This one here is a weak acid. And then I want you to write the Kb expression for, let's do methylamine, so CH3 NH2. And I'm going to quote a value on table 21. So table 21 actually lists for you the pKa's and pKb's. I'm just going to quote these values for you so you know how we're going to work with these numbers. So the pKb for this methylamine was given to me as 3.34. So pKb is 3.34. While the acetic acid here, the pKa from the same table, the pKa, right, A for acid, is 4.76. Now, to be sure, when you're writing the expression, we don't actually need the number, but as we walk through it, I'll show you what else we can do with the numbers. So, we might start off here thinking a simple equation, a simplified equation. So this one here is acetic acid. The simple Bronsted-Lowry definition is this one here is going to release a proton. So by ditching a proton here, that H on the end here is the easily removable proton. We talked about here the acetate ends up in resonance, and we end up getting our acetate ion. That is sort of a simplified picture of, as I donate a proton, that's what I become. We don't write a Ka expression for the simplified equation. We need to always write the complex equation. To go from the simple to the complex, on the acid side, it's sort of like adding water to both sides. So what's going to happen here is actually our equation is acetic acid is not alone. It's dropped into a solution of water, so there's a lot of H2O around. And basically, it doesn't just throw the proton out just randomly swimming around. It's actually going to take its proton, and it's actually going to pass it over to water. We always just do one proton transfer, so the mole ratio will always be 1 to 1. We're going to still end up with our acetate, but it's the H plus and the water that's going to end up forming our hydronium. Hydronium is synonymous with H plus, so that's perfectly fine, but that's more thorough of an equation. As we get to tomorrow's lesson, setting up some ice tables again, we would definitely want to have the complex equation before you do anything else. At this point here, we're ready to do our equilibrium constant. So for acetic acid here as an acid, this is the reactant. It should be products over reactants. The Ka is going to be the hydronium multiplied by the acetate divided by the acetic acid. Right? Again, on the table, what they've given you here is not just the Ka, they've given you the P of Ka. We're going to see in today's lesson, P of anything means power of this, and the power of Ka here actually stands for, pKa is actually the negative log of Ka. we're going to start introducing logs. Logs are the inverse operation for exponents, and instead of carrying around these huge negative powers here, that log there is going to get rid of that power problem. And then with that negative here, it's just by convention, we usually have a pH ruler that the smaller the number, the more acidic it is, that negative helps accomplish that. So if I know that the pKa is 4.76, we're going to do more of this in today's lesson. How can we get just the Ka? How do we know the actual number? What you want to do is you want to go anti-log of negative pKa. I need to bring the negative over, and I need an anti-log to get rid of the log. So the exponent is the inverse of a log. So you go to shift log. Anti-log of negative, in this case here, 4.76, gives me my Ka constant. This number, we have the expression for it, but this number for our current acid is 1.7 times 10 to the negative 5. In some sense here, even the water equation, you can think of, well, this is water on the left side. This is water behaving as a weak acid. So water has an acid constant of 1 times 10 to the negative 14, whereas my acetic acid has a constant of 10 to the negative 5. Because this one has a relatively larger Ka constant than water, this one is a better acid than water. Still overall weak. Both of them are still in equilibrium. They don't go 100%. In fact, that's a nice hint for ourselves. Whenever we deal with Ka, Kb expressions here, we're always dealing with weak things. I'll show you what it would look like with a strong thing later on. But pretty much it's weak. We know in general the numbers are going to be tiny, but still relatively, I can say this is larger than the Ka for water. So this is a stronger acid. So acetic acid is actually a stronger, still I want to emphasize it is a weak acid. It does not ionize 100%. It's a stronger weak acid than water. Right. Let's do exactly the same on the other side here. This is a little bit strange. This is one of our unusual compounds. This is actually an amine. An amine here has this NH2 functionality. We'll do a whole chapter on organic to learn that later on. This one here is already neutral. Normally, I would pick up protons until I'm neutral, and then I would stop. But in this case, if you actually take a look at the methylamine structure here, even though overall I'm neutral, overall I have no charge, the nitrogen group actually does have a lone pair. So what ends up happening here is actually in the presence of H+, the nitrogen is actually just going to form a coordinate bond with the H+. We will end up forming CH3NH3+. Again, when I'm interested in writing these Kb expressions here, I don't just want to show you, oh yeah, this one here picks up the proton, equilibrium. Still try to color code it for you here. Right. Dative bond here, coordinate bond, right? Overall, it's going to be charged. Remember, there's not a lot of H+ in solution, right? Water has the ability to self-ionize, but it's a really smidgen, it's a really, really tiny amount. So instead, what we're going to do is we're going to write the complex equation. The complex equation, so that's in some sense here a simple equation. To get to the complex equation on the base side, it's sort of like adding hydroxide on both sides. And this is just sort of algebra for us to actually get from one equation to the other. We're not actually adding hydroxide. It's just going to get us to the right final answer. So we have our methylamine, CH3NH2. Instead of writing, oh, it's stealing a proton, the H+ and OH-, it's telling me it's actually stealing from water. There's a ton of water around. We're going to still end up with our methylamine. A little bit strange. It's protonated now. So CH3NH3+. I've gone up by an H and I've gone up by a charge. And it's actually the water that's actually going to leave behind this hydroxide. So plus OH-. Again, when we do our ice tables in tomorrow's lesson here, we will always want the complex equation, because when you're thinking of this one here as a base, it's easier to track if I actually have a column for hydroxide versus just indirectly, oh yeah, if I lose H+, it's sort of like becoming more basic. So there's my complex equation here. Let's write out the Kb expression. The Kb expression, products over reactants for my complex equation. It's the protonated methylamine, CH3NH3+, times OH- all over CH3NH2. Right? And again, on the table, you have this value quoted for you. pKb is 3.34. Again, the lower this number, the stronger it is as a base. This number 3.34 is actually lower as a base than the acid of acetic acid. So this is actually a stronger base. So let's just calculate here. What is the Kb constant? The Kb, you can write it the same way, 10 to the negative, or you can even write in words here, anti-log. Just don't forget to go negative 3.34. And we'll see more of this power stuff in today's lesson, but just for completeness sake, the anti-log of negative 3.34, this one here amounts to 4.5 times 10 to the negative 4. This is essentially a Kc. This is a products over reactants. Overall, yes, it is tiny. Overall, the bulk of it actually stays on this side. There's actually really little that actually manages to get over. But relatively speaking, this is a like a number that's closer to 0. It's a bigger number, so therefore this is a stronger base. Okay. I didn't practice with you so far in this setup, sort of Ka of the conjugate to compare to Kb of the partner, but we'll do that later on. In today's lesson, I just want to introduce to you a little bit more of the math here. We're going to revisit our scales here on pH and pOH. In some sense, we already have some familiarity with this. We talk about a pH. Oh, yeah, it is a ruler at 25 degrees. 7 is the dividing line. So 7 is actually a neutral pH. I want to emphasize the temperature here. Later on, they're going to ask you, oh, how come I'm at pH 6 and I'm still neutral? Probably you're not at 25 degrees. Based on our scale, so we typically ballpark it between 0 and 14. It's not impossible for pHs to go into the negatives, go actually above 14. But as we're going to see, because pH and pOH, both of these are what are referred to as logarithmic scales, even though it looks like everything is evenly spaced and evenly stepped, in fact, like the earthquake scale, every step is 10 times harder than the one before. So a pH of 6 is 10 times more acidic than a pH of 7. Going from 7 to 5, that may look like, oh, just twice the difference here. Going to a pH of 5, while pH 6 was 10 times more acidic, going to pH 5 is actually 100 times more acidic. We're in a base 10 system, so that's easier to work with. So by the time I get really, really into the acidic region here, really small pHs here, it's getting increasingly hard. 0 is like 10 million times more acidic. You have 10 million more concentration than H+. It's getting really hard to get into 100 million, right? So it's getting really hard to get pushed into the acidic region. Although, do note this one here. If you actually look at the numbers for pH, pH 7 to pH 6, pH 5 to pH 4, we had said the acidic side is going to be farther away from 7. So just terminology-wise, I can say as the pH decreases, that's actually a way of saying we're actually getting more acidic. Sometimes people accidentally go, oh, pH, oh yeah, I'm going to look at H+, that is true. But pH is just the name of the ruler. Well, if my acid scale decreases, I'm getting less acidic. Well, no, in this case here, if my pH number is actually getting smaller and smaller, 7 to 6 to 5 to 4, we're actually getting more acidic. And sort of the opposite is true here. If I have my pH increases, that means on the ruler I go 7 to 8 to 9 to 10 because I'm heading more towards the basic side. pH increases is a way to say actually more basic. So just watch out for that. I'm going to also introduce to you a pOH scale. It's also going to be logarithmic here. It will be sort of in relation to the pH scale, but let's start off with the one that we're more familiar with. In some sense, what I want to target is a lot of the KWs, KAs, KBs we've been dealing with so far, they have all these 10 to the negative, right? It's not impossible to use exponential notation and actually write that easier, but if there were a way to sort of get rid of those powers, sort of re-express it in a little bit easier fashion, I'd go for that. So that's our lesson today here. When chemists put this letter here, P, in front of anything, that P is shorthand for negative log. The log part is going to undo the exponent part for me, and the negative is just for convention. Because I want the really tiny numbers to be acidic, I want the negative. That's just going to flip the scale around. So just by definition here, you can memorize these ones here. So pH, it's the, you can say in words, it's the power of H. So I am watching H+. The P stands for negative log, so it's negative log of H+. H3O+, well, how do I undo this then? Let's just do some algebra here. What I would need to do is I would need to push the negative over. I need to undo the log. So therefore, I've written it a couple times already now. The H3O+ is actually the anti-log of negative pH. Most people do remember to take anti-log, shift log, but don't forget it has to be the negative because that's the first thing that I kick over. Right? So this pH is by definition. pH is the negative log of H3O+, and then if I want to undo that, it's going to be anti-log of negative pH. In a similar way here, remember P anything is just negative log. What if I introduce to you a pOH scale? A pOH scale is basically power of OH, so it's going to be negative log, and I'm actually going to be watching the hydroxide concentration this time. I'll draw you the ruler for pOH later on, but there we go. pOH is the power of OH. That's just a ruler. Depending on where I land on this ruler, I could be acidic, I could be basic. And if I sort of undo it here, I can go hydroxide is the anti-log of negative pOH. I can, just for completeness sake here, sometimes they write it like this, but just also remember it's anti-log of the negative of pOH. Okay. Let's just practice through here, just for example. Let's say I'm given, we have a solution. Let's start off with 1.5 molar HCl. All right. Throughout this chapter, you're gonna save yourself a lot of time. If anytime you're given like a chemical like this, ask yourself what this is. Is this an acid? Is this a base? Is this a salt? If you identify it's an acid or base, is it strong or weak? Because depending on your answer there, what you're going to do next is actually going to be different. So in this case here, hopefully you remember, well, we know it's an acid because it currently has an H, and HCl, our stomach acid, is actually a strong acid. Strong acids are actually really easy to work with because HCl, it's going to be one-way arrow. We're going to end up forming H plus and Cl minus. That's the simplified equation. Just looking at our molarities then, if I have 1.5 molar HCl, because we are 100% ionized, we're going to 100% break up. The 1.5 molar box is going to completely be gone, forming 1.5 molar of H plus and 1.5 molar of Cl minus. Now, Cl minus is just going to be a spectator. I'm not going to worry too much about it. In this case here, I've now been able to calculate, okay, here's the 1.5 molar concentration for the H plus. Very, very acidic. If, just for argument's sake here, if you try to do a Ka for this expression. So let's think. If I just try to do Ka, Ka is supposed to be products over reactants. I shouldn't be doing to the simple equation, but I'm just going to show you what happens here. So Ka is supposed to be products over reactants for an equilibrium. I know it's already not an equilibrium, so already that's a problem. So if I were to define a Ka, the constant for the acid, the products are 1.5 times 1.5, but wait a second, this one here is 100% associated. Essentially, the HCl is going to approach 0. And if I take a number, whether it's 1.5 times 1.5, those are fairly tiny to begin with, but as I divide by a number that's getting smaller and smaller, I really don't have any reactants. What that's going to say is the Ka is just going to be very large. It's going to approach infinity. It's not even a nice number. So that's why usually when you're asked, state the Ka expression, oh, here's the pK, usually it's going to be weak, because in this case here, because it's for a strong thing, it's almost nonsensical. The value is just so large. Right? So back to this calculation here. We have our pH. It's not so bad to look at, right? H plus is 1.5. There's no ugly exponents, things like that, okay? What I want to do is just sort of pictorially, let's pretend we're going to drop in 1.5 molar HCl. Well, what am I dropping this HCl into? Well, I'm dropping it into a vat of water, right? Now, I'm going to ignore the dilution for a second here. Basically, what happens here is water is going to come in, and it's actually going to separate the H and Cl. I'm adding enough, so the concentration, even in this water, is still going to be 1.5 molar. So the HCl ends up breaking off to become H plus and Cl minus. In fact, what we know is we actually have 1.5 molar H plus in solution. We know it's acidic, because this one here was a strong acid. But remember from our self-ionization of water, because there is also water around, it knows there's going to be a ton of acid around. But from the water equation, we had this expression, Kw is supposed to be H plus times OH minus. We know at this point here, at first, from yesterday's lesson, we had started off, water has the ability to self-ionize. It's like 10 to the negative 7. It's 0.0001 molar of all these equal amounts. It's neutral. What we're doing now is we're artificially beefing up the 1.5. So we're coming in and we're adding a ton more H plus. In this case here, now the H plus is now something like 1.5 molar. Sure, you could say 1.5 plus this 0.0001. Well, that's so tiny. We'll practically just say 1.5. And in this case here, because there was no mention that temperature was different, we can assume that this constant here, it still has to hit 1 times 10 to the negative 14 at our standard temperature of 25 degrees. So that means as the H plus has climbed from the 10 to the negative 7, as it's gotten bigger to get to 1.5, the OH minus had to have gotten smaller. It's going to have shrunk. Definitely, it's going to be really tiny. But water, even though I have seemingly, it should just be H plus, water would still have a really, really slight possibility. Every time water breaks up, it's going to form an H plus and hydroxide. It's going to always self-ionize, always replenish a little bit of hydroxide. You will never have a water solution that is pure H plus or pure OH minus because of the self-ionization. So what we can do here is we can say, all right, I increase the H plus. It's an inverse relationship. What's the hydroxide concentration for me to still hit this constant? Note this constant, although it's tiny, it's not 0. So what I'm going to do here is I'm going to go 1e negative 14 divided by 1.5. So that tells me, as expected, the OH minus, it is tiny. It was tiny to begin with, 10 to the negative 7 for a neutral solution. But now, as you increase the H plus, you made your solution more acidic. The OH minus has actually dropped to 6.7 times 10 to the negative 15. So while, yes, water has the ability, let's write this down in words, even in an acidic solution, like this 1.5 molar HCl, water will self-ionize, right? Water doesn't need the acid. Water will self-ionize to regenerate or recreate. If we had lost all the OH minus, I don't see any OH minus, water itself will replenish that amount, will regenerate OH minus, so that the H plus, whatever it is, 1.5 in this case here, OH minus still equals to the Kw at the given temperature. So remember, an acidic solution is not one that just has acid particle, it's just you have more acid than base. That's acidic. All right, so the acid number was 1.5. 1.5 is way bigger than OH minus, fine. So H plus is actually bigger than the OH minus, and it's actually that greater than, that actually tells me we are in an acidic solution. The 1.5 number wasn't that hard to look at. The OH minus, however, is like a 6.7 times 10 to the negative 15. Scientific notation actually does a good job with this, but this one here, if you can appreciate it, it's like 0.0, like lots of zeros before you get the 6.7. What I'm going to do now is I'm going to use this pH or pOH. Let's put me on the ruler. Let's get rid of this exponential problem. Let's introduce a logarithmic scale to make these numbers look a little bit nicer. So since this one here is the H plus, I can then do pH. Really simple definition. Power of anything is negative log of that thing. All you're going to punch in your calculator is negative log of 1.5. So negative log 1.5. This one here gives me negative 0.18. Right? Remember, pH was my ruler. I had roughly ballparked it between 0 and 14. Because HCl is a strong acid and 1.5 is a decent molarity of it, we've actually pushed into the negative pHs. That's totally fine. We are very acidic here. Right? It's a strong acid. Okay. So 1.5 wasn't that bad to look at. Negative 0.18 also not that bad to look at. I'm going to see more so on the pOH side. pOH is actually going to be negative log of the hydroxide concentration. I'm going to show you sort of the math behind the scenes here. Negative log of 6.7 times 10 to the negative 15. Normally what you would do is you just plug in the numbers and you get the answer. I'm just going to show you one middle step here. You might remember from your math classes here, there's some log rules that when you have log of two things multiplied, that's essentially log of A plus log of B. At the end of the day, it sort of has to do with exponent rules where sort of if you multiply a to the m, a to the n, it's a to the m plus n, right? So multiply becomes a plus. The log rules, which is the inverse, has a very similar relationship. What I'm going to do is I'm going to show you one middle step, which I don't normally show. Negative log, it's like taking negative log of 6.7 and then adding a negative log of negative 15. Right? Oh, sorry, 10 to the negative 15. Right? So I'm taking my 6.7 as my A, 10 to the negative 15 as my B. Because of the log rule, it's log of the first thing plus log of the second thing. It's just that I want a negative log, so negative log of the first thing plus negative log of the other thing. So I'm just going to show you mathematically what this does. Negative log of just the base number, 6.7, ends up giving you negative 0.826. Let's just say 83. And then the other case here, negative log of 10 to the 15, negative 15, just gives you 15. So you see we've done it, right? I've gotten rid of this ugliness of carrying around a huge, huge power by taking a log. Sure, there was a negative to sort of flip the way the ruler landed. But there we go, 15 minus a 0.83, give or take a little bit of rounding. My pOH is now currently, if you had just typed in negative log, type in 6.7 e negative 15, you would have gotten this 14.17. So on the pOH ruler, I haven't really introduced it here, but the pOH ruler also has 7 as a dividing line. Numbers that are tinier than it are actually going to be basic, so pOH of 0 is basic. Numbers that are big like this, I have up to 14. I've actually breached the 14.17. That actually means acidic. Yes, I am watching hydroxide on the pOH scale, but the bigger the number as pOH increases is actually becoming more acidic. So 14.7 is also very acidic. Just because I restated the number doesn't suddenly make the solution, oh, we were acidic before and now we're basic. No, we have to be acidic. So again, just for terminology's sake here, you can say as the pOH increases, we actually get more acidic. All right. What I wanted to show you with this math here is, in terms of significant figures, normally with the number 6.7 times 10 to the negative 15, it's only the base numbers that are significant. This number here is a 2 sig fig number. I've just given you one example. I haven't generalized this, okay, but I'm just going to show you here. In general, when you take a negative log of some base number, some number between 1 and 10 in proper scientific notation, negative log of it will always end up as decimals. It will always end up as negative 0 point something. The part that's insignificant, it's insignificant in terms of meaning. It's important there to put my decimal point in the right place, but this one here doesn't give me any meaningful digits for my measurement. And what's going to happen is when you take the negative log, yes, we take care of that problem 10 to the power of, we get rid of that exponent. This insignificant part always ends up to the left of the decimal place. So just as a conclusion for you here, even though I'm writing the number as 14.17 or 0.18, the significant part, the base number part, will always end up, after you do this negative log work, it's always going to end up on the right-hand side of the decimal place. So that's a conclusion I want you to take away. So in terms of significant figures, in terms of how many digits to keep, even though I'm going to still write the whole thing, 14.17, it's important to locate me on the which ruler I am at. But basically, the conclusion I want to take from this, if you have pH, if you have pOH, I'll throw in, you can have pKa, pKb, because p of anything is negative log of this thing, pKw, right? All of these p whatever, in this case here, the significant digits, significant figures are after the decimal place, right? So just watch out if they give you a pH or a pOH here. If I have a number, okay, my pH is 0.18, 2 sig figs, fine, easy to read. 14.17 is a pOH here. It may look like a 4 sig fig number, but no, the significant part here was only the part that was after the decimal place. So this is actually a 2 sig fig number here. Okay, so I just wanted to introduce to you those scales, the pH, pOH. We worked through an example here. I'm just going to show you a nice little summary on this side here. Basically, we've been introducing some terminology. Well, we can define solutions in terms of how much H plus there is. For my example, the H plus was 1.5 molar. We can use the Kw expression. We had found 6.7 times 10 to the negative 15. Basically, anytime I have one of these numbers, I can relate it to 3 other terms that also say the same thing. We know our solution was acidic. I gave you my acidic number, it was 1.5. What was our connection between H plus and OH minus? Hopefully you remember there here. Well, for this connection here, I'm just going to erase the number for argument's sake. For this connection, it was actually through Kw. Kw was the H plus times OH minus. You can memorize 1.0 times 10 to the negative 14 if we're at 25 degrees. So anytime you give an H plus, water will make sure of it to always self-ionize to replenish a little bit of hydroxide. There's not a ton of it. We've just introduced 2 other terms here. Going from H plus, if it wasn't a really nice looking number, I can say pH is the negative log of H plus, or you can say negative log of hydronium. pOH, in a similar fashion, is negative log of the OH minus concentration. If you want to undo it, basically remember what we did is we pushed the negative back over. The anti-log will get rid of the log for me here. Going from pH back up to H plus, I actually want to take the anti-log, 10 to the negative of pH, or going the other way here, 10 to the negative of pOH. So I can go to and from H plus to pH and vice versa. And there is one other connection here. And that last connection here is, what about between pH and pOH? I'm going to show you a derivation. We're going to end up with pKw is actually pH plus pOH. Okay. So let me just show you that there. You don't need to reprove this to me every time, but I'm just going to just do it once for you here. Essentially, if you take a look at the Kw expression, Kw was supposed to be H plus times OH minus. Water will self-ionize. It's going to replenish some H plus and OH minus. What if I took negative logs of both sides? So that's the operation. Take the negative log on one side. Negative log of Kw is going to be the negative log. I'll color code this for you here. Negative log of H plus times OH minus. We're going to use that same log rule from earlier. Log of 2 things multiplied is log of the first thing plus log of the second thing, minus log of H plus, added to another minus log of OH minus. I just distributed that negative log back over. And then hopefully you're able to say to me here, well, hey, this is negative log of Kw. Let's call this pKw. Sometimes Kw is also a very times 10 to the negative big number. pKw is actually equal to negative log H plus, oh, that's just pH. And negative log OH minus, oh, that's just pOH. And what we're going to actually do here, although this is a general relationship, right, this is true for all temperatures, what we're going to sort of force on it is we're going to say, let's pretend we are at 25 degrees. if we are at 25 degrees, the kW is 1.0 times 10 to the negative 14. If you try doing what is negative log of this 1 times 10 to the negative 14 number, you will actually end up with 14. So sometimes they actually just say 14 is equal to pH plus pOH, but that one also is only true at 25 degrees. In fact, if you want to compare the pH and pOH scale, these two always need to add to give 14. At 25 degrees, we're familiar with the pH scale, so this is 7. There's on your notes page, it actually gives you some room to do this as well, but while I have it. So 7, this is the sort of neutral point for both scales. The H plus is equal to the OH minus. As you start stepping lower than that, 7 to 6 to 5 to 4, we had said this side here was acidic. For a pOH scale, going 6, 5, 4, 3, right, smaller numbers like that, this one here actually means basic. Where is basic on my pH scale? Oh, my basic pH here is actually anything bigger than 7. So basic is actually there. So somehow this part, the basic side on the pH scale, the above 7 pH, actually corresponds to the below 7 on the pOH scale. So what I'm going to do here is I'm going to pretend your pOH scale here is a meter stick. I have the 0 marking, I have the 14 marking. I want you to just reverse this meter stick here, flip it left to right, so that my pOH scale, I'm still watching OH, it still has 7 as the dividing line, but have the 14 up here and have the 0 down here. In that situation, we had already said, okay, 7, 6, 5, 4 on the pOH scale here, that was basic. And now what I've done is I've lined it up properly here. Let's say I have a pH of 8 because it lines up here with the pOH of 6. 8 plus 6 equals 14. Perfect. I obey it. What if it's pH of 9? pH of 9, 9 plus what has to give 14? Well, it has to be 5. So basically pH and pOH, because of the relationship between H plus and OH minus, they're sort of reverses of each other here. And therefore, if I flip it around here, if I have numbers that are bigger than 7, pOH of 8, 9, 10, that would be the acidic side, and in a similar fashion, the acidic side would match up with the pH less than 7 side. So pH of 4 lines up with pOH of 10. These are just many different rulers, many different ways of representing exactly the same number. All right? So let's just highlight some details here. So I have the complete box here. If you have one of these numbers, you know all the other relationships here. We had just derived here pKW is equal to pH plus pOH. When we're assuming 25 degrees, this one here is actually 14 at 25 degrees. So if they're lazy and they go, oh, pH plus pOH, 14 minus this, it gives you the other number, it's because they're assuming 25 degrees. Remember, previously we also had a relationship, KW was equal to the KA times the KB, when these ones here were conjugates of each other. In a very similar derivation here, I'll let you derive it for yourself, the pKW is also pKa of the acid plus pKb of the base. All right. So there are some practice questions here we'll come back to. I just want to flesh out some of these other key details first. Quick note about significant figures. We had said the sig figs are after the decimal place. So while you still need to write the entire number, right, make sure you have enough digits after. So therefore, for pH, right, P anything, pH, pOH, pKW, pKa, pKb, for all of these ones here, the significant figures are after the decimal place. Okay. Why do we even need a pH scale? Again, I'm going to emphasize here this is at 25 degrees. At 25 degrees, our special temperature has 7 as our dividing line. I don't know which one of these is 7. 7 actually refers to neutral, but again, that's temperature dependent. If I have heated it up, we saw that the H plus and the OH minus actually changes. We saw that we can have pH 7, pH 6, 5, 4, 3, like that. We're getting more acidic as you go down this way. So more acidic. We had talked about the terminology. pH decreases means more acidic. That's what the negative log has done for us. I want to emphasize they always like asking you this one here. pH is a logarithmic scale. Logarithmic. So basically it's based on powers of 10. pH of 6, like we said, is 10 times more acidic than 7. pH of 5 is 10 times more acidic. It's 100 times more acidic than 7. Going the opposite way here, Let's just do different numbers. How does a pH 9 solution compare to a pH 12 solution? Going from here, we know we're actually going to be more basic. Every step is 10, so times 10 times 100 times 1,000. So we can say more basic times 1,000. So that actually means my hydroxide concentration is actually up by a factor of 1,000. It has increased by a factor of 1,000. Or you can say the H plus hydronium has actually decreased by, well, I'm using decreased already. The language already is dropping, so decreased by a factor of 1,000 as well. Okay. So that's how we do our scale here. A couple other notes before we practice through some problems. Some notes here. As the pH increases, right? So let's think about what that means. On the pH ruler, yes, I'm watching H+, but as the number itself gets bigger, that actually stands for more basic. You can translate that for yourself. As we get more basic, the pOH actually decreases. pOH was sort of a reverse of the pH scale. It was a take the meter stick and flip it left to right. And then we'll also make one other note here. When the pH increases by 1 unit, so one step on this logarithmic scale, it could only go up by maybe 0.5 or 0.8, doesn't really matter. But when the pH increases just by a single unit, we can say the H3O plus, the hydronium, decreases by a factor of 10. So not only does this pH, pOH here solve the problem of I don't want to carry around such big negative exponents, it makes the numbers look easier. It puts me easier between, let's say, 0 and 14, roughly speaking, and helps me identify whether we're acid or base. So I'm actually going to leave this question for you to try out here. So they give you, oh, here's the pH. If you know the pH, can you find the OH minus? You can either anti-log negative pH and then get to hydroxide. You can go 14 minus and then anti-log that. Because this is a square, you can get anywhere around you want. pOH here, given an acid solution, we'll practice this as a warm-up tomorrow. There's one question I want to end off with. This one here is a little bit more interesting. What is the pH of water at 50 degrees? So notice that we are not at 25 degrees anymore. Is the solution neutral, acidic, or basic? Well, they just said we are water, right? You can even qualify that, oh, it's pure water. It's not acid, it's not base. We should say neutral. A neutral solution here should have H plus equals to OH minus. So neutral solution here, remember water will self-ionize to always replenish some hydroxide, right? So H plus is equal to OH minus. At 50 degrees, well, we were used to Kw being 1 times 10 to the negative 14. We had derived yesterday. Basically, as you heat up the temperature because it's endothermic, actually I need to write this back down here so that we can actually answer this question here. Because our self-ionization is actually endothermic, as you go from 25 degrees to 50, our stress was I increase the temperature. I shifted this equilibrium to the right. What's going to happen is I'm going to end up, the H plus concentration goes up, and the OH minus concentration goes up. We had said in yesterday's lesson here, well, if the acid particle goes up, it's more acidic. Why does the water sour on me? Well, no, because again, every time the water actually breaks up, it becomes more acidic and also more basic at exactly the same rate. So in terms of pH now, how do we say more acidic? More acidic is lower pH. How do we get more basic at the same amount? You can say lower pOH. So yes, the pH and the pOH are responding. We're not quite the same acidity as we were at 25 degrees, but they change at a 1-to-1 ratio. As long as they're equal to each other, the solution is still neutral. So what can we do here? We can use our Kw expression. Our Kw is supposed to be H plus times OH minus. Because we are neutral, these two things are X. X times X are supposed to give you Kw. The Kw this time is 5.5. Remember, we have a table of Kws in table 23. I'm just going to take a square root of them there. Let's find what the hydronium concentration and the OH minus concentration is. So 5.5 e negative 14. I'm going to take the square root of this number. X is equal to 2.3 times 10 to the negative 7. That is the molarity of H plus and OH minus. Let's go back and reread the question. They wanted to know what is the pH. Well, the pH is actually the negative log of this H plus. So negative log of 2.3 times 10 to the negative 7 gives me here negative log of this answer is 6.63, right? And now my dividing line, it used to be 7 is neutral. Now my dividing line has actually pushed over to 6.63. Now 6.63 is actually neutral. Anything less than it is acidic. Anything greater than 6.9, 6.8, which previously would have been acidic, is actually going to be basic. So my neutral line has actually shifted at this temperature, right? So practice through a few questions there. We'll pick it up there. Thanks, guys.